Hello everyone, welcome to the Innovate UNO 2020 virtual event. And thank you in advance for taking the time to watch this video. First, let me introduce myself. My name is Murat Tanil and I'm a PhD candidate in the Department of Civil and Environmental Engineering. Little bit about my background. I received my undergrad back in 2017 at University of New Orleans, and then I received my Master's in Science degree in 2019, again in University of New Orleans. Then I start my PhD, and currently I'm working on my dissertation under the supervision of Dr. Katrin and Dr. Mathieu. This presentation will take about 15 minutes, and it is divided into two sections. Section 1 is going to discuss the development of real-time drainage monitoring system, and in Section 2, I will cover the SWMM model for the UNO Lakefront campus. Also, I want to mention the collaboration between civil and electrical engineering departments at the University of New Orleans. This collaboration between two departments significantly improved the process flow and productivity in our research. So let me start giving you some background information. The University of New Orleans is an urban university situated along the beautiful south shore of Louisiana's Lake Pontchartrain. It is bounded by the city of New Orleans and Mississippi River to its south. The university is located in the Gentle Neighborhood District, and as a result of being situated below sea level, the area is drained by one of the city's 24 pumping stations. Located in the coastal region of Louisiana, the university's 250-acre campus often experiences extreme rainfall events that can overwhelm the drainage capacity and cause water quality concerns. And for the past few years, the university's administration has received complaints regarding the flooding in particular areas of campus. To address these issues, our team initiated the research on the development of real-time drainage monitoring system and SWMM model for the UNO Lakefront campus. Our work started in November 2019, beginning with the design and construction of the wireless sensor network to collect the storm event data in the drainage system. So let's move on to our vision. The overall vision for our research is to develop a cost-effective stormwater management modeling system that can be scaled and implemented in larger urban environments. This system will become an advanced technological solution for engineers and developers to address urban stormwater management concerns through green infrastructure programs that require and promote low-impact development design practices on new development and redevelopment projects. The specific goal of this project is to develop a calibrated SWMM model of our campus that integrates real-time next-right rainfall data to drive the model and forecast potential stormwater flooding. The development of this type of system will allow our research team to assess the condition of stormwater drainage system on our campus and identify the source of local flooding problems and design and analyze the efficiency of low-impact development alternative solutions. So, what do we need to accomplish first in order to reach our specific goal? In general, we have two primary objectives to reach our specific goal. First step is to develop and calibrate cost-effective wireless sensor network for monitoring pipe flows. As you can see from the figure on the right side that shows the big picture of our system, we can see how wireless sensor network operates and provides real-time water flow and water quality data from the drainage system. So far, we developed the wireless sensor network system, and now we're working on the optimization and calibration of the system. Second step is to develop and calibrate SWMM model for UNO campus. Again, from the big picture, we can see how SWMM model for campus for our campus will be developed. Besides the real-time drainage monitoring data, NextRAD, next generation radar rainfall data, is also integrated to our system to calibrate the SWMM model. This big picture is significantly important, and it clearly shows major components and data flows in our system. Now I would like to look at the research method, which consists of several phases. In the first phase, we work on the development of real-time drainage monitoring system. It is also called wireless sensor network or IoT network, Internet of Things. And nowadays, IoT is getting famous every other day, and we see that devices are being connected to the internet. And anyhow, in general, the wireless sensor network has the capacity to measure, compute, and communicate environmental data to other systems where they can be translated into useful information. The sensor nodes that we design and develop from scratch can be seen on the top right corner. It measures the water level underneath the manhole and sends the data to the back-end cloud server where the data is stored and processed. Then it is directed to the front end in which the results are visualized and displayed on the website. And in the next few slides, I will walk you guys through the platform and explain the features, the details on the platform, and the capabilities of the platform that we designed from scratch again. As I mentioned at the beginning of the presentation, we initiated this research back in 2019, November 2019, so it's been a year, 12 months. And if you take into consideration 3-4 months of literature review, we were able to finish the first phase of this research in less than a year, and hopefully we will be done with this research in the next year at the completion of the UNO SWMM model, calibrated SWMM model. Anyhow, I would like to look at each sensor node, each sensor box in details and see what is in the box. So if you look at the top right corner, you will see that blue light that flashes when the data is being transferred. Anyhow, that device is the microcontroller. We tried different type of microcontroller, including Raspberry Pi, Arduino, etc. But at the end, we end up with the Boron device, which has the cellular connection capability that transfers the data via cellular connection to the cloud platform. And you can see the cellular flexible antenna on the top right corner. Also, we do have the lithium-ion battery pack underneath the circuit board. And you can see the ultrasonic sensor on the bottom image, and the fully adjustable linkage that's anchored into the brick wall in the manhole. So now we're looking at the cloud platform that I mentioned in the previous slide. This is just a screenshot of the dashboard where you can see the live radar image as well as the precipitation forecast at the bottom right corner. So everything in this platform is in real time, but if you want to go look at the historical data, look at the historical storm events, you can go to reporting section and then you can look at the specific timeline and pull up the data, and you can even visualize the historical data and export it in the Excel spreadsheet format. I don't want to get into too much details because it is a complex platform and I have a limited time. I run out of time right now, but you can also go to device management and add as many devices as you want. Right now we have only one device. If you look at the image, you see that the red icon, and that shows the geolocation of the device that was installed. That's the engineering building. And if you were able to looking at the website, if you can pull up the website, you can hover over this icon and you can see the live data from the device. And if you click on that device, that's the screen that you're gonna get in the next slides. I'll go back in the previous slides in a few seconds, but I wanted to show you what you will get if you click on the icon on the sensor. So you will get the water level data in real time. During that time, the device was not installed, so there was no data in the there was no real-time data. But once the device is installed in the field, you can start looking at the water level data instantly. You can check the battery life, and then you can check the temperature and humidity. That distance is also the distance between the sensor and the water, because the ultrasonic sensor measures the distance between the target and the sensor head. We just wanted to edit here just to check the water level if everything was correct. Anyhow, you can also see the precipitation over here on the bottom right chart. With that being said, now we're going to take a look at the second stage of our research. As I mentioned at the previous slides, in the second stage of our research, we are working on the development of calibrated SWMM model for our campus. First, I would like to start with the simple explanation of SWMM. Let's take a look at figure 5 that shows the water cycle or hydrological cycle, and it describes the continuous movement of water on, above, and below the surface of the earth. This is what exactly SWMM tries to simulate. SWMM is most widely used numerical model for simulating urban runoff and drainage, and it stands for Stormwater Management Model. As you can imagine, all the details about specific watershed are often unavailable or incomplete. A typical SWMM project will have hundreds to thousands of subcatchments and more than 20 parameters for each subcatchment. Modeling and simulating this environment requires a lot of parameters to demonstrate complicated relationship between rainfall and runoff. Calibration involves changing these parameters to make sure the predicted runoff matches the observed runoff. Next, let's look at the calibration process. Typical SWMM calibration procedure includes the following steps. First, model is set up, creating watershed of interest. Then, simulation is performed by applying rainfall data. The resultant runoff predictions are then compared with the observed data. This is then followed by the sensitivity analysis to help find which of the countless parameters are sensitive enough to cause changes in the output. Depending on the results of the analysis, the sensitive parameters will then be updated and the process goes on. So calibration of the SWMM model will ensure the predicted runoff is the same as observed runoff. As I said before, we are going to use our real-time drainage monitoring system to collect the observed runoff values from the field, and we will use those parameters to calibrate our SWMM model for UNO campus.